10 scientific questions everyone should know the answer to. Scientific research continues. The level of public education is on the rise. Surrounded by technological marvels, from wearable electronics to communication satellites, we're supposed to be pretty darn smart and knowledgeable about science, aren't we? The problem is that okay, not we, but many, are terribly ignorant when it comes to basic scientific knowledge. Only 53% of people know that the Earth orbits the Sun in 1 year, and only 59% of people know that the first humans and dinosaurs lived at different times, not like in The Flintstones. Only 47% of people accurately answer that 70% of the Earth's surface is covered by water. Rainbow. Obviously, although we've come a long way, there are still many steps ahead before we reach universal scientific literacy. But for those of you who get desperate to change the subject when someone mentions the Higgs boson, supercomputers, or starts arguing that dinosaurs had feathers, there is a good reason to read this article. This article is about 10 scientific questions that everyone should know the answers to. Why is the sky blue? The sky is blue. We see blue or blue skies, white feathery clouds, or heavy thunderclouds. But we still like blue skies better than overcast skies. European scientists have found that light from the blue part of the spectrum has a positive effect on our emotions, making us more responsive to emotional stimuli and adapt to emotional difficulties. But let's not get distracted. The sky appears blue because of the so-called scattering effect. Sunlight has to pass through Earth's atmosphere, which is filled with gases and particles, which are the barriers that sunlight knocks against. If you've ever held a prism in your hands, you know that light consists of a bunch of different colors, each with a different wavelength. Blue has a relatively short wavelength, so it passes through this filter more easily than colors with longer wavelengths, and as a result scatters more widely as it passes through the atmosphere. This is why the sky appears blue when the sun is high in the sky. At sunrise and sunset, however, the sun's rays must travel a greater distance to reach their position. This negates the wavelength advantage of blue and allows us to see other colors, often red, orange, or yellow. You may ask, why isn't the sky purple? Purple has an even shorter wavelength. But the solar spectrum is uneven and there is less violet, and the eye is more sensitive to blue and less sensitive to violet. What is the age of the Earth? Earth. Probably not a single New Year's Eve on our planet goes by without someone seriously saying, "I can't believe the Earth is turning 2015. Or 2016, or 2017. The Earth's true age has long been the subject of fierce debate. As early as 1654, a scientist named John Lightfoot, whose calculations were based on the biblical book of Genesis, proclaimed that the Earth was created at 9 a.m. Mesopotamian time on October 26 in 4004 BC. In the late 1700s, the scientist Count de Buffon heated the small copy of the planet he created and measured the rate at which it cooled, and already based on this data he estimated the age of the Earth at 75,000 years. In the 19th century, the physicist Lord Kelvin determined the age of the Earth to be 20 to 40 million years. But all this went down with the discovery of radioactivity. Subsequent calculations showed the rate at which different radioactive substances decayed. Earth scientists used this knowledge to determine the age of Earth's rocks, as well as samples from meteorites and pebbles brought back from the Moon by astronauts. They looked at the decay state of lead isotopes from the rocks and then compared it to a scale that showed how lead isotopes change over time. The Earth formed about 4.54 billion years ago with an error of less than 1%. How does natural selection work? Fish like the age of the Earth. The theory of evolution, first developed by biologist Charles Darwin in the mid-1800s, is a separate topic that people don't know but love to discuss. Nowadays, opponents of the theory of evolution are trying to remove it from the curriculum in schools or have children study creation science, in addition to the theory of evolution. And there is one idea that the opponents of evolution cling to: natural selection, a central concept of Darwin. Understanding this idea is quite simple. In nature, mutations, that is, permanent changes in the genetic program of microorganisms that will later distinguish a species from its predecessor, occur by chance. But evolution, a long process in which animals and plants have undergone many changes over many generations, is not random. As a rule, changes in organisms become more widespread over time if they help the organism survive and reproduce. For example, imagine that some bugs are green but become brown due to a mutation. Brown bugs blend in better with their surroundings than green bugs, which is why they are not often eaten by birds. More of them survive, they reproduce in greater numbers, and these changes become permanent rather than temporary. Eventually the beetle population will turn brown. But this is the simplest option. In practice, however, natural selection takes average rather than specific representatives, and it is not very easy to isolate this process. Will the sun ever go out? The sun, if you think that the sun for a person stops shining when they go through hard times in their life, that is not the case in reality. The irony is that the reality around us, the light of the sun, the singing of the birds, is more enduring than our fragile senses. Unless you were born 5.5 billion years later. At that point, the sun, like another star, like a giant thermonuclear reactor, will exhaust all the hydrogen in its core and begin to burn hydrogen in the surrounding layers. This will be the beginning of the end of the sun. The core will shrink and the outer layers will expand, and the star will become a red giant. In the final outburst, the sun will fry the solar system with a blast of heat that will turn even the cool surroundings of Pluto and the Kuiper belt into a celestial sauna. The inner planets, including Earth, will be sucked up by the dying giant or turned into ash. However, unless humans colonize the solar system or other stars, no one will even know about this final inferno. The sun, which is already halfway through its lifespan, is gradually heating up, and in a billion years will be 10% bigger. The increase in solar radiation will be enough to vaporize all the Earth's oceans, leaving us without water and the rest of the joys of life. How do magnets work? Staples for a long time, magnets have been considered something of a miracle. And this is unfortunate, because it is quite simple to understand how they work. A magnet is any object or material that has a magnetic field. That is, a bunch of electrons in it are floating in the same direction. Electrons like to form pairs, and iron, for example, has a lot of unpaired electrons that are easy to hook up to some hangout. This is why objects made of solid iron, or with lots of iron in general, will be attracted to a powerful enough magnet. Substances and objects attracted to magnets are called ferromagnets. People have known about magnetism since time immemorial. Magnets are found in nature, and medieval travelers learned how to magnetize steel compass hands, that is, they created their own magnetic fields. Such magnets were not particularly durable, but in the 20th century, scientists developed new materials and chargers that led to the creation of powerful permanent magnets. You can create an electromagnet from a piece of iron by wrapping it with electrical wire and attaching its ends to the poles of a large battery. What causes rainbows? Rainbow. There is something special about this atmospheric phenomenon that has aroused the awe of humans since ancient times. According to the book of Genesis, God put a rainbow in the sky after the great flood and told Noah that it was a sign of agreement between me and the earth. The ancient Greeks went further and decided that the rainbow was the goddess Iris. True, her figure was ominous, she heralded war and retribution. Over the centuries, great minds, from Aristotle to Descartes, have tried to figure out what process produces the rainbow's many colors. Now, of course, scientists know it well. Rainbows are caused by water droplets that remain suspended in the atmosphere after a good downpour. The droplets have a different density than the surrounding air, so when sunlight hits them, they act as tiny prisms, breaking the light into constituent wavelengths and then reflecting them back. An arc of visible spectrum color bands is born, which we can see. Because the droplets must reflect the light back to us, to see the rainbow, you have to have your back to the sun. You also need to look from the ground at an angle of about 40 degrees, which is the deflection angle of the rainbow, that is, the angle at which it refracts sunlight. It's also interesting that when you're in an airplane, you can see the rainbow as a disk, not as an arc. What is the theory of relativity? Albert Einstein. When someone mentions the theory of relativity, they usually mean two theories at once, a special theory and a general theory developed by physicist Albert Einstein in the early 1900s. Regardless of the degree of our reverence for Einstein, people far from science have little understanding of his theories. Einstein himself came up with a good way of explaining it. When a man sits with a pretty girl for an hour, it seems to him that a minute has passed. But let him sit on a hot stove for a minute, and it will seem longer than an hour. Everything is relative. It seems to make sense, although the details are, of course, more complicated. Before Einstein, everyone pretty much assumed that space and time were motionless and monotonous, never changing, no matter from which point on Earth you looked at them. But Einstein used mathematics to prove that the absolute view of things is an illusion. In fact, space and time change. Space can contract, expand, bend, and time flows at different speeds depending on the speed of an object or the force of a gravitational field. In addition, the manifestation of space and time can depend on a person's point of observation. Imagine, for example, that you are looking at an old ticking clock. Now place that clock in Earth's orbit so that it moves at a tremendous speed compared to your position on Earth. The clock in orbit will tick slower. The clock is slower because of the phenomenon of time dilation. Space and time are actually parts of the same whole spacetime, which can be distorted by gravity and acceleration. Therefore, if an object moves very fast or is affected by a very powerful gravitational field, time for that object will go slower compared to an object that is not affected in the same way. Mathematical calculations can be used to predict how time will slow down for fast-moving objects. This probably sounds strange, but it's true. GPS satellites, which depend on accurate time measurements to map the Earth, are a good example of this. Satellites fly around the planet at about 14,000 kilometers per hour, and if engineers had not adjusted their clocks to account for relativity, Google Maps would be wrong by almost 10 kilometers during positioning in a day. Why are bubbles round? Bubbles, yes, bubbles aren't always perfectly round, as you must have noticed if you've inflated them at least once. But bubbles tend to be spherical, and you may notice that even the longest ones tend to become round. The fact is that bubbles are essentially thin layers of liquid whose molecules are held together by a phenomenon called cohesion. This creates surface tension, a barrier that prevents objects from penetrating it. But that's not the only force that acts on this layer. On the outside, air molecules apply pressure. The most effective way for the fluid layer to counteract these forces is to take the most compact form, which is a sphere, if you calculate the volume-to-area ratio. Remarkably, scientists have long ago learned how to make non-circular bubbles, cubic, rectangular, by stretching a thin layer of liquid on a wire frame, whatever. What are clouds made of? Clouds. We hope we don't disappoint anyone, but clouds aren't really a mixture of ice cream and angel feathers. Clouds are a visible mass of water droplets or ice crystals, or a mixture of both, suspended above the Earth's surface. Clouds arise when moist, warm air rises. As it rises higher and reaches the cold zones, the warm air cools and the water vapor condenses into tiny water droplets or ice crystals, depending on the temperature. These droplets and crystals remain clumped together due to the principle of cohesion, which we talked about above. This is how a cloud is born. Some clouds are thicker than others because they have a higher density of water droplets. Clouds are a key part of our planet's hydrological cycle, in which water constantly moves between the surface and the atmosphere, alternating between liquid, solid and gaseous states. Without this cycle, life might not exist on our planet. In 1803, meteorologist Luke Howard identified 4 basic classifications of clouds, which today have Russian and Latin names. Cumulus, or cumulus clouds, are the piled lumpy clouds we often see in the sky. Cirrus, or pinnate clouds, which means hair in Latin, are light feathers at altitude, as thin as strands of hair. Flat and unsightly clouds are stratus, which means layer in Latin. There are also nimbus clouds, low and gray rain clouds. However, there are slightly more subspecies and varieties of clouds, as well as their mixtures. Why does water evaporate at room temperature? Glasses. We humans are used to thinking of reality as a nice stable place where different things stay in their places unless we want to move them. But reality is different. If you look at water on a molecular level, the molecules look like a pack of puppies vying for the best position on their mother's belly. When a lot of water vapor collects in the air, the molecules bump and stick to the surface, resulting in condensation on the outside of a cold drink on a humid day. Conversely, when the air is dry, the water molecules in your cup can stick to other molecules floating in the air. This process is called evaporation. If the air is dry enough, more molecules will transfer from the cup to the air rather than escaping from the air into the cup. Over time, water will lose more and more molecules, and eventually you will end up with an empty cup. The ability of molecules from a liquid state to jump out into the air and stick to it is called vapor pressure, because jumping molecules exert force, just as a gas or solid exerts pressure on something. Different liquids have different vapor pressures. Acetone, for example, has a high vapor pressure, meaning it evaporates easily. Olive oil, on the other hand, has a low vapor pressure and is unlikely to vaporize at room temperature.